when x is less than 0, we have 0. So we put the condition in first, which is x less than 0, comma, the actual value, which would be 0. Now we put in the next expression. So afterwards, it would be x being less than 1. So we have x less than 1. And then we put in whatever number we have, which would be x squared. So now we put in x squared. Then the third condition, which is x being greater than 1. And then we can just put in whatever we have here, which is 2x minus 1. And that would, so something's missing. Ooh. Oh, yeah. So this is what I forgot. Between every multiplication, you can't just be like 2x. You have to be 2 asterisk x, because Maple is stupid and it can't read that. But yeah, now we have our piecewise. And something else you might realize is we didn't actually put in an x greater than 1 in here, because if you don't add a condition for the last one, it just does otherwise. Now, what we can see is that we can also substitute in a number. So maybe we wanted to do minus 1. So we have subs x equals minus 1, comma f, because we want to sub it into f. And then we evaluate it. And what we see is that it still has this piecewise, but all of the x's has been replaced with a minus 1. And the reason for that is because subs literally just substitutes it in and doesn't actually evaluate it. If you want to evaluate it, you have to put the eval keyword in front. So now it substitutes it, then evaluates it. So we get 0, which we know is true because minus 1 is less than 0, so it would return 0. And then we also have some commands which are for simplifying expressions. So for example, we can factor out a polynomial such as x squared plus 5x plus 6, and then it would give us the factors. Or we can tell them to expand something such as x plus 1 to the power of 3, and then it expands it for us. We can also expand other things such as trigonometric expressions. So we might have cos A plus B, and interesting. Wait. Oh yeah. So yeah, that's a reminder. Whenever you set something beforehand, so we set a to pi somewhere, it essentially just keeps it. So whenever you're moving on to the next question, if you don't want it to affect what you're doing, you should try to restart. And that just removes every variable that you set previously. So if you do f, you will no longer get this piecewise function. So if we expand cos A plus B, we get the expansion. Of course, you can also use it to simplify things. So if we simplify, give it an expression such as ln of x squared plus 2 to the 5 over 2, you'll see that it takes this 2 to the 5, which is 32, and then divides it by 2 for us and gets us 16. And then what we can do is we can also simplify rational functions by using normal. So if we put in 1 over 1 minus x minus 1 over x plus 1, we would get this, which would be the combination of these two, which you would usually see in partial fractions. And that's pretty much it for functions, and we will start going through calculus. So obviously we'll start with limits. That's probably what you started with in calculus. Limits, they're quite easy to do in Maple. You write limit, you write in the expression that you want, maybe sine of x over x, and then we want the limit as x approaches 0, and that would give us 1. Of course, we can also do other numbers, such as infinity, and we know that sine x over x, as it approaches infinity, gets us 0. And then what we can do is we can also take the limits of left and right hand sides. like, for example, the absolute value of x minus 2 over x minus 2. And then what we can do is we give it a number such as 2. Then we specify whether we want it on the right or the left. So if we do right, it will give us the right-hand limit of 1. But then if we write left, it will give us the left-hand limit of 1. And if we don't specify, but it has a different left limit and different right limit, it's just going to give us undefined. So we can also do derivatives, and the way we do that is we have a function. So let's assign y exp x, so that's e to the x, as we said before, and then we multiply by sine x squared. So one difference between expressions and functions, you use the diff command for expressions, but for functions, we have e to the x times sine x squared. We have to use capital D, and then we put in f in brackets. Now, the difference between these two is that when we diff an expression, it's still an expression. You'll see that there's no arrow here. But if we diff a function, it still becomes a function. So, well, of course, obviously, we can also substitute in values by just using brackets, and we get when x is equal to 1. So we can also do higher derivatives. So the way we would do that is we would do diff, and then we would put in an expression such as y. And then maybe to do the second diff, you would add an extra x as a argument, and that would get you the second diff. If you wanted to do the third diff, you would add an extra x. But it might get a bit messy once you have 5 ongoing, right? So we can simplify this by using a $sign. So if we do $5, we'll see that we get the same thing, because this means something in Maple. It means repeat x 5 times. So repeat what is before the $sign, whatever's after the $sign times. So if it means repeat x 5 times, that means this is equivalent to doing 5x's like this. So we also have implicit diffs, and what that means is we just take an implicit function, and then we can just differentiate it. So the way we would do that is we use implicit diff. We put in an expression like x squared plus y squared equals 1. Then we put in whatever variables we want to diff it by. So say we want to diff it by y and x. Something's wrong. Let's diff y x. Okay. It's because this variable seems to be already assigned, so we have to restart. And then we should be able to do this now. Yeah, so we get the implicit diff with y and x. And then, of course, we don't see an arrow here, so it means that it's an expression. So if you wanted to substitute in a specific point, we would have to do it with subs. So to do multiple different variables, we first double one of the variables, so maybe x equals a half. We do a comma, then we do the other variable, square root 3 over 2. Now we put in the expression, which would be d. And that just substitutes x equals a half, y equals square root 3 over 2 into d, and we get this. So
this screen looks like this.
Ooh.
Sorry, we just got to fix some things up briefly.
You did this now?
Huh?
Did you?
I didn't even realize until like now. Which one's that?
Should be fine.
Okay.
Right.
Continue. I'll see.
Yep, so we have the implicit diff of x to the 3 plus y to the 3 plus 1, which is equal to x times y plus 1 to the 3. And then we specify what variables we want. And that would give us the derivative of this function. So we just do... why isn't it showing everything? It's like...
oh, shit, that's annoying. Try again, yeah.
I don't think we can.
Alright, it's fine.
Yeah, I think maybe we record later. Just do it. I might just do this recording again at home or something.
Nah, no way, bro. We can't do that.
Yeah. So what we can do is we also can find minimas and maximas of different functions. And the way we do that is we use minimize if we want to find the minimum. And then we can give it a function such as sine x plus cos x. And if we don't give it a range, it just finds the global minimum. But if you specify a range such as x from minus pi, so we might see a dot dot here. That means go from the first number and then go to the number that's after the 2 periods. So that means find the max between minus pi and pi. And then we can also maximize functions the same way, such as e times e to the minus x squared times x. Ooh. Yeah, so something you might see is that I put maximize with an S. So this is American spelling, so we actually have to use a Z. So if we put in Z, we get it. So that's something that's very important to notice. Use a Z, not an S. But yeah, we can also integrate. So we have f colon equals x squared times sine x. And then what we can do is to integrate, we use int. Now we can put in the expression f, and then we put in an x. And that integrates it up for us. So what you can do is you can also integrate with a range. So the way you would do that is you would let x equal to some range such as 0 to pi, and the way we do a range is just with the double dots as we did before. So this gives us a definite integral from 0 to pi of our function. And now we're up to collections of expressions. So by collections of expressions, we mean something like a sequence. So, sorry. A sequence is a list of objects in Maple which are separated by commas. So we have 3 these. That's a sequence because it's a bunch of things separated by commas. So we can also do the thing before. So we have the $sign in here, and we have 3 repeated 4 times. This would give us a sequence of 3, which is just 4 threes, right? Like that's what we expected. Then we can also use seq as a keyword to declare a sequence. Then what we can do is we can give a range of a pronumeral such as k. Now what we can do is we can put in an expression such as k squared. So what we see is that the sequence here is 3 squared, 4 squared, 5 squared, 6 squared. So it goes through every number between this range, 3, 4, 5, and 6, and then does this function, and then returns it as a sequence. So we also have lists. A list is just a sequence, and then you put square brackets around it. And then we also have a set. A set is a sequence. You put curly braces around it. And the difference you might see is that we had 4 threes here, but then it collapses to 1 3, because obviously a set doesn't have any repeating elements. So if there's already a 3, there's not going to be a second 3 if you try to add another one. Now, what we can do is we can also see that you can assign it to variables, since you can assign basically anything to variables in Maple. So let's say that we assigned S1 to this list right here. We know it's a list because there are square brackets. And the thing about lists is, unlike a sequence, you can actually look at specific elements. So if we do S1 and then we put brackets, then we put in a number such as 1, it means get the first element of the list. So what you might see is that the lists in Maple are 1 indexed and not 0 indexed. That means that this, if you do S1 of 1, you would get the first element, and if you put in 2, you would get the second element. If you put in 3, you would get the third element, and so on. What you can do is you can also get a range, so maybe with all elements between 2 and 4, and that would get you a list from 2 to 4. Now what we can also see is that we can also get maybe the second element, and what we can do is we can use colon equals to reassign a value, so let's say 15, and what that does is it replaces the second element with 15. So something cool about lists and sequences is you can take them and then do a sum or multiplication of them. So let's say that we have a list right here, maybe L1, which is defined by 3, 7, and 18. We can use add and then k plus 2, maybe k plus 1. Now we assign k to our list, and what it does is it takes the first element, puts it into this function, which is 4. Then it takes the second element, puts it into this function, adds it to what we already have. So 7 plus 1 is 8, and then it adds it to 4, so in total we have a 12. Now it takes this 18, puts it into this function, which we get 19, adds it to what we already have. 12 plus 19 is 31. So the cool thing about this is you can put in anything. Like if you want to just sum all of the elements in the actual list, we can just put in k because it adds 3, 7, and 18. But then we can also maybe, for example, square all of the numbers before adding them. So that gets us 3 squared plus 7 squared plus 18 squared. And of course we can confirm this by doing 3 squared plus 7 squared plus 18 squared. And we would get the same number because that's exactly what it's doing. And what we can also see is that we can use the word MUL to multiply it together. So if we replace these with multiplication signs, we'll see that we get the same number because that's exactly what it's doing. Now, what you might see is that there's also sum and product. And the reason we don't usually use them is because if you try to do sum and then you assign k to a list, it gives you an error because it doesn't take lists. It only takes in ranges. So you can do 1 to 10, and then it gives you the sum from 1 to 10. But the thing about sum is you can also include infinity. So from k's 1 to infinity, if you add them all together, you get infinity, right? And then of course we can do other things such as a half to the k, which gets us a geometric sequence from powers of k for 1 to infinity. And if you know that sum, you'll see that it's equal to 1. So it lets us work with infinity. But then it also lets us work with pronumerals. So if we let this, for example, be 1 to n, it gives us a general formula with n. So that's what sum's used for. And of course, we can also do this with products. So the main thing is, if you want to use a list, you use add or mul. And if you want to use a range, you use sum or product. Now, there are also functions to manipulate structures. So what we can do is we have L1 right here. And we can use NOPS, and what NOPS does is you just put in a list, maybe L1, and then it finds how many elements there are. So L1 has 1, 2, 3 elements, it will return 3. We also have op, and what op does is it turns any list into a sequence. So it takes the list and then gets rid of the square brackets on each side. And why we might use op is because it makes sequences, so we can take apart lists and then we can combine them with other lists. And that would get us a sequence and then a sequence, which we combined because we can combine sequences, but I don't think we can combine lists. And then we put square brackets around it to make it a list. So we can also declare a list with variables, maybe x, x squared, and x cubed. Now what we can do is we can use subs, and what subs does is if we say, for example, specify an x to be equal to I, what it does is we then specify a list, and for every element in the list, it's going to substitute in what we ever put for x. So you might see that here we have x, so that would give us I. X squared would give us -1, and x to the 3 would give us -I. So we can do this for other numbers such as pi as well, or 16 on 3, etc. Then we also have map, and what map does is if you do map, you can give it a function such as cos, and then you give it a list. So maybe take the list before. What it does is it puts that function through every element. So what it does is we have a function here, we have 16 over 3 here, puts it into a cos. We have 256 over 9 here, puts into a cos, and so on. So that's pretty much it for the collections of expressions. We'll be moving on to complex numbers and equations by Fred here. And is there a way to fix this? Like,
Give us a second just to try and fix up the stream.
So we add.
The second part is like it's the path cutoff. The first part is just like it's maple stuff. It is a bit scuffed.
Okay, I think that's just it. Is that? We might want to move this to the back. Is that a thing? Oh, it's because it's this one. That's it. Yeah.
Scroll back and then see it pop up.
Shows everything.
Are we supposed to send out the links to people? Or do we do it after? Is it before or after? That's good.
Yeah. Maybe we just do it after.
Okay. So moving on is we're going to be looking at some complex numbers and equations. So as you know, we represent that as the square root of -1, and as with any real numbers, we can also add, multiply, and do all of those normal operations with complex numbers. Okay. And there are two different functions that we do use. Eval-C, we use that to evaluate exact Cartesian form, and eval-F is for a numerical operation. Okay, so let's assign Z1 to equal 2 plus 3 times I. And if we copy out this function, eval-F, Z1. As you can see, we sort of get like a numerical approximation, 63.0, but that is, of course, still an exact number. If we gave it a different number, that would make it, say, for example, like an irrational number, it would give out a numerical approximation. And if we instead did eval-C of Z1, we get the exact complex number 2 plus 3i. Okay. And a lot of your basic complex number operations, such as real, imaginary, argument, modulus, and conjugate, these are all built in within Maple. So again, if we want the imaginary part of Z1, we just simply call im of Z1, and that would extract out the imaginary component. Okay, and same with the real component. That's just going to be RE of Z1. For the others, we have the argument function that just simply calculates the argument of our complex number. That's going to be the inverse tan of 3 on 2. And if you want to evaluate that to an approximation, again, we can use our eval_f command and put in our previous answer percentage, and that would get out numerical approximation. Okay. For the modulus of a complex number, we simply just use the absolute value function. That also works for complex numbers. So absolute value of pi plus I, that's going to be the square root of pi squared plus 1. Okay. And the last one is just the conjugate function. That just simply returns the conjugate of a complex number. So 1 plus I, and that should get us 1 minus I. Okay. The one thing with complex numbers is we can also form equations, and they are expressed in the form of the left-hand side equals some expression on the right-hand side. Okay, so if we have equation 1 and we set it to 2x plus y equals 5, notice in this example we have, instead of assigning like an expression to a variable, we have now assigned an equation to a variable. Okay, and again, equations, they can be added with other equations, and normally how you solve simultaneous equations, Maple can do the same as well. Okay, so if we copy this code over, so we're adding on 23 equals x, that equation, to our original equation, equation 1, and we're dividing by 3. Unexpected number, equation 1. There we go. And as you can see, we get a nice final equation out. And the last thing is we can use the LHS and RHS to find the left and right hand side of equations. Okay, so RHS of equation 1, that's just simply going to be 5. One thing that's quite useful with Maple is we can solve for exact solutions. So for example, if we want to use the solve command, this can be used to solve many algebraic equations. So a simple case, if we want to solve 3x plus 4 equals 5, sorry, equals 5x, so 3x plus 4 equals 5x. Normally, if you just have one variable in your equation, Maple knows which variable to solve for. So in this example, we just have x in our equation, and Maple knows just to solve for x. Okay. Whereas if we have more than one variable, so say for example we want to solve the quadratic equation, ax squared plus bx plus c equals 0. Notice we have different variables a, b, c, and x. If we just hit enter here, notice Maple just outputs a bunch of gibberish. So essentially here we have to tell Maple which variable to solve for, and in this case we want to solve for x. Okay, solve for x, and as you can see we get the two sides of the quadratic formula. So that's for cases where we have more than one variable. And again, we can assign this into a list. So if we assign our solutions, wrap it around some brackets, that's going to return the solutions inside a list. Okay, and we can do the same operations as before. S of 2 would get out the second element. There we go. Okay. Okay, so exact solutions. Now, again, if we have two equations and like two unknowns, normally you would solve those two equations using simultaneous equations. Maple can also do that for you. So if we have equation 1 and we set it to equal 2 times x plus y equals 5, and we have equation 2 and we set it to x minus y equals 4. Okay. We can tell Maple to solve these two equations simultaneously by again using the solve command. And this time we have to wrap our two equations around braces, so we chuck it inside a set. And we have to tell Maple that we are solving for which variables we're solving for again. We're solving for x and y. Okay, and as you can see, it nicely solves the two equations for us. Okay, and if we again use the assign command, that's going to set the solve variables invalid left side. Okay. Oops. Solving for expressions other than function names. And let me just get rid of this. Okay. What is going on here? In solve. Okay, let's do this again. Solve equation 1 and equation 2, and that should get us these solutions again. Solving for other than names of functions. Okay, let me restart here. Might be because of we have set different variables. So if you look at the left-hand side, we have a bunch of different variables already assigned. And to just make things clean, we want to hit the restart command, and that resets all of the variables. And let's reassign these. So we assign equation 1, assign equation 2, and we solve for it again. Yeah, and there we go. Okay. So oftentimes when you run into problems, it probably is because we have too many variables assigned. We just got to hit the restart command and resets everything. Okay. And if we want approximate solutions, this is the command fsolve. That's going to be used to find approximate solutions. So if we want to fsolve the quadratic equation x squared minus 2 times x plus 2 equals 0, and we set x. Notice we don't get any solutions out because we have to tell Maple that we want complex solutions. Okay, that's going to be involving chucking a third parameter complex, and as you can see, when you hit enter, Maple nicely solves out the equation. Okay. And we can also assign it a range of solutions that we want. So say, for example, we want to solve x cubed minus 3x, minus 3x squared, and we want to plus 2x. And so we're solving for x, and we want solutions ranging from -1 to 3 on 2. That's just going to generate out the solutions in between the range. Okay. Yeah, and that concludes the part for complex numbers and just solving equations in general. The next part is going to be on plotting. Okay. The first part is just simply plotting a single variable. So if we want a function like y equals x squared and we want to plot it on Maple, let's see how we're going to do that. Okay, so let's hit the restart again. The command that we use for plot is just the plot command. Okay, And if we want to just graph the generic parabola, y equals x squared, we just chuck in x squared. And the second parameter is the range of x values that you want. Okay, so let's say that x ranges from -1 to 3. And as you can see, we get a nice parabola where the x values range from -1 to 3. Okay. So if we want to plot tan x, so tan x, where x ranges from 0 to 2 pi. We can also specify a third parameter, and that's the list of y values that we want to output. Okay, so if we want y values from -10 to 10, notice that we get the nice tan graph, and the y values range from -10 to 10, and it gets cut off after. Okay. And the last thing is we can also plot multiple curves on the same graph. And to do that, we first need to chuck all of our equations inside a list. So suppose we have, suppose we set the graphs to be a list of these two equations. And we call the plot command again on graphs, where x ranges from -2 to 4. As you can see, we get the two curves on the same graph using lists. Okay. Now, sometimes equations, they're given to you in parametric form. So that's the case where x is in terms of a third variable t, and y is also in terms of that third variable t. Okay. And we're going to see how we can plot these ones. So normally, the format is we just give it in the given the x function and given the y function, and specify where t ranges from. Okay. So, say for example, we want to plot the unit circle in Cartesian form. That's again going to be the plot function, and this time we have to chuck all of our parameters inside a list. Okay. And the unit circle is just going to be the cosine t, sine t, and where t ranges from 0 to 2 pi. Okay, and as you can see, we get out a nice, really nice unit circle. Okay, and again, if we've already used our variable t like previously, and we try to do the same thing, we are going to get an error. So if we set t to equal 16, and we try plot the same thing after, as you can see, we get an error, and the error stems from the fact that we've already assigned the t variable previously. Okay, just make sure the variables that you're using, you haven't assigned them to anything before you actually calling the command. Okay. And the last two types of plots that you can get are polar plots and implicit plots. Okay. And these two aren't built into Maple. You actually have to first import the plots package. Okay. And again, remember, to import a package, we use the with command, and inside the with, we have the plots. Okay. And as you can see, we get a list of different extra functions that we can call. And to hide this, we just add a colon in front and hit enter. Yeah. Okay. So the first thing is our polar plots, and that's called by the command polar plot. And inside the parameter is, the first parameter is going to be our function in terms of theta. Okay. And the second one is where theta ranges from. Okay. So, for example, let's call polar plot of the function I equals 1 minus cos of theta. And theta ranges from 0 to 2 pi. Okay. Hit enter, and as you can see, we get a nice graph depicting our equation I equals 1 minus cos theta. Okay. And as you notice, the background of the curve is also a bit different than what we have previously. This is the polar curve, and they just add in like different arguments and radius just to make things look easier. And the next type of plot is the implicit plot, and that is oftentimes we're given an equation in implicit form. So, for example, the unit circle x squared plus y squared equals 1. To plot that, we would use, again, the implicit plot. Okay. So implicit plot. Let's say we're trying to plot the hyperbola x times y equals 1, where x ranges from -1 to 1. Actually, let's do -2 to 2, and y ranges from -2 to 2. Okay. Hit enter, and this gives us a nice hyperbola. We can also increase the range to make it look clearer. So -10 to 10, hit enter, and that would get us a nice looking hyperbola. Okay. Okay. And the last topic is going to be on looking at linear algebra. Okay, so that's everything related with vectors and matrices and all of that. So the first thing is we're going to look at is how to create vectors in Maple. Okay, so let me just restart everything again. Restart. So in Maple we use the less than and greater than sign to define vectors, and all of our elements will be wrapped around these two signs. Okay. And there are two types of vectors that we can define. One's the column vector, and the other is the row vector. The first one is the column vector, and we use a comma to separate out each element, whereas a row vector, we use the vertical bar to separate each element. Okay. So just a quick example, if we want the column vector 1, 2, 3, 4, we just wrap it around these signs, and since we want a column vector, we use commas to separate each element. Okay, hit enter, and as you can see, we get a nice column vector out. Okay. Whereas row vectors, instead of using commas, we used vertical bars. So 1, 2, 3, 4. Hit enter, and we get a nice row vector out. Okay. So two different ways we can define vectors. Now, creating matrices, there are two different ways you can think about creating matrices. The first way is you can think about matrices as columns of column vectors, or you can think about them as rows of row vectors. Okay? So notice in the first example here, we have vertical bars separating out each vector. In this case, we have simple column vectors which are separated by vertical bars. So this would depict the case where we have columns of column vectors. Okay. So if we output this out into Maple, let's call this A equals this. As you can see, we get this nice square matrix. Okay. And one thing to notice is that the first element here, this column vector, represents the first column. Okay. The second element, this column vector, represents the second column, and the third vector, 369, represents the third column. And again, we can separate columns using these vertical bars. Okay. So this is the case where we have columns of column vectors. Second way we can define them is through looking at rows of row vectors. Okay. So if we copy the second one over, hit enter, as you can see, we get out the same matrix. But the key difference is instead of these elements are instead row vectors. So the first element here, 1, 2, 3, that represents the first row. Second element, 4, 5, 6, second row, and same with the third element as well. Okay. And remember, with rows, these are separated by commas. Okay. And hence we get a row of row vectors. Okay. So two different ways we can define matrices. And there are many functions that come with the linear algebra package. For example, one is going to be linear solve. That's the one that is really useful for you. Okay, so we can import that package again with just calling with linear algebra. Okay, enter. Yeah, and again, you see, look at all of these different functions that we can call on matrices and vectors. And again, if you want to hide this, just chuck a colon in front and hit enter. Okay. Okay, one of the things we can do is extract rows and columns from matrices. That's just simply using the row command and the column command. Okay. So let's define a matrix M. Let it be this square matrix 1, 2, 3, 4. And the first parameter is the matrix that you're calling the row command on, and the second command is the which row that you want to take. Okay, so let's take the first row, and that will get us 1, 3 as we expected. Okay. And the same thing is the same with columns. We can call column M, get the first column, and we get the 1, 2 as we expected as well. Okay. Okay, now, next thing is we can define a series of special matrices. So here we have like 4 main types of special matrices. We have identity matrices, diagonal matrices, matrices of equal elements, and lastly is the zero matrix. Okay. And all of these commands come with the linear algebra package, so you have to make sure that you have imported this package first. Okay. So if we want identity matrix, a 3 by 3 identity matrix, we simply call the identity matrix command and pass in 3, hit enter, and we get the nice diagonal of 1s. Okay. If we want these diagonal numbers to be different numbers, we call the diagonal matrix command instead, and pass in what numbers we want inside. So if we want 1, 2, and 3, notice in this case we get a diagonal matrix with the diagonals 1, 2, and 3. Okay. The next one is we're looking at matrices of equal elements, and that's going to be called by the command matrix. The first 2 parameters of matrix represents how many rows and columns you want inside your matrix. So if we want a 2 by 4 matrix, first parameter is going to be 2, second parameter is going to be 4, and the third parameter is what we want our element to be. Okay. So if we want our element to be 1, we're essentially creating a matrix of a 2 by 4 matrix with elements 1. Okay. And the last thing is creating the zero matrix. Okay. That's again called by the zero matrix command. And if we want a 2 by 4 zero matrix, pass in the parameters and we get a nice zero matrix out. Okay. Okay. Now, next thing we are going to talk about is Gaussian elimination. You guys might have covered this in lectures, maybe not. But if you do get up to this, solving this by hand is really tedious after you've done like a lot of practice. So Maple really helps out by just doing it for you. Okay. So again, this comes with the linear algebra package. So you first need to define that. Okay. So let's first define a matrix A. And if we want to find the row echelon form of this matrix through Gaussian elimination, we simply can just call the command Gaussian elimination and pass in our matrix. and that would reduce it into the form that you want. Okay. So this essentially eliminates the need to do like tedious hand calculations where like you can easily make like a silly mistake. Okay. And if we want to find the reduced row echelon form, we just call the reduced row echelon form and pass in our matrix A, and that most of the times would reduce it into the identity matrix. Okay. Not all the times. And the last thing that we are going to look at is linear solve. Okay. This command is actually really useful. In 1A and Math 1B, you're going to be solving a lot of matrix equations, and solving them by hand would often be like quite tedious. So this linear solve command just solves it for you without having to do any tedious commands. So if you don't know, matrix equations essentially involves this equation AX equals B, where A is a matrix, X and B are vectors, and you want to solve for X. Okay. So again, you would first need to import the linear algebra package. Okay. And suppose we have the matrix A equals this thing over here, and we have the vector B equals this vector here. Okay. And again, suppose we want to solve the matrix equation AX equals B. To do this in Maple, we can simply call the linear solve command. Linear solve. The first parameter is going to be your matrix, and the second parameter is your vector. And hit enter, and that would nicely solve the matrix equation for you and give out your X vector. Okay. Yeah. And that brings us to the end of the workshop. Does anyone have any questions? We'll be free to help around, come around and help you guys out. Okay. Any questions? Nah? Okay. But yeah, that wraps it up. Good luck for your lab tests or your final exams. Yeah, wish you the best. Question?
So we can come around if you have any questions. Like, just raise your hand and we'll try to answer it.
you're still
I got injured.
from honors?
Yeah.
Oh, come on, man. That teacher lesson? What happened? Who did it?
This dude.
Yeah.
You know Nathan Moore?
Thank you all for coming. This is the end.
I was supposed to give
We'll
it.
probably be losing to the right schools.
Wait, so what was the name?
What?
What's wrong with you? I beat it the first 2 times, and on the 3rd time, it went. Well, it wasn't major. It's like. If you have if you know the technique.
Smart man.
What?
It's smart.
About the slides, I haven't really got them in my email, so...
Yeah, we're not.
We're gonna send it out.
Yeah.
We're gonna send it out.
We know we haven't sent them because we haven't sent them.
I know, I was really anxious, so I was like, oh,
It's like we have to send them, right? Like we've been here the whole time, so we haven't sent them. Like we'll try to send it by tonight.
Yeah, definitely.
What info?
Huh?
What info?
You should have like when you registered, you should have put your email, right?
Wait, register for what?
This event.
Oh, I just turned off.
Oh,
Wait.
yeah. So
Yeah, do you have Facebook? No, I don't use Facebook. I probably should.
okay, yeah. In our thing we have a
You scan this. We get free $2.
Yeah,
Oh,
so
okay.
for every scan we get free money. So that's why we make them do it. But then of course we also want to send resources through there.
Oh, what resources?
Mainly the slides, yeah. So yeah.
The only reason is you might get paid for the extra hours that goes out. I think so, but I don't. I'm not too sure. Because what? Still what? Yeah, just prep something, I guess. I don't know. I never prepared.
I think there's a default eval. Is it? So like just eval?
Yeah.
Like this one? Just
Yeah.
that. What is it? 1 plus.
Probably don't have a common use of that.
1 plus 1. Oh, if we, okay, so if we do like 1 on square root 2, I just don't know. I guess it just gives you the exact form, pretty much. Not approximation, yeah.
Oh,
If we have
okay,
eval
that makes
f, yeah, approximation to 10 dp's. And if we want more dp's, 20, I think, yeah, do it like that. And it gives you more.
Can you? Okay, what if I do?
Like x squared.
Oh wait, what?
I don't do that. I don't think I do that.
Oh, whoops.
Don't have to look
You have that core strength, bro. You got that. You see that core strength. Yeah, I saw the Russian guy.
Is that legit or what?
Where he's got mad core. Only the Russians.
Only
do that.
Russians.
No.
Only Russians, bro.
Only Russians.
Doesn't work.
Okay, you wanna go now?
That's true, right? Probably is a bit transformative, to be honest. Probably is a lot. Careers. Do it with your laptop. Don't you less strong?
I love time.
I'm ready for careers fair.
Chris Fair.
Wait, okay.
Oh.
How about this?
Wait. No.
So if we do this,
Time to
start
meet.
just first, right?
This.
And then gradually just add strength. Until and no like just and then no Come on, I don't want to be recorded. Can you delete that?
Yeah, I can do it. Yeah. Sorry, I just wanted to record Fred because like every time he does an arm wrestling, like I want to record it. So no, but yeah, I understand. I'll delete it right now. I'll also delete from recently deleted, like because like I don't really, yeah, like I want to value you more, you know?
William was a bit camera shy.
I'm not camera shy, I recognize that having
Can I like view it from your perspective? So like it's like him, it's just
yeah,
him.
if it's just him, it's fine.
So like maybe your arm will get it, is that okay?
Just get his face.
Okay.
Just his face.
Just get his face.
No?
No, continue. Are you sure?
Oh, no, what's wrong?
Oh, you wanna try? I'm not gonna try. What are you? Oh my god, this is crazy.
Are you have to do this and wait, how do you do that?
Wait.
Don't do that. That's dangerous.
You're pulling my arm. It's crazy.
I don't know the technique.
Well, I don't know if you either. I'm just pushing you.
Just his body behind it.
Why? How about you just do it to a certain?
That is
That is really like is.
Yeah, put your whole body behind it. Boom.
Like,
The body's just there so you don't break your arm. It's kind of like it's a safety. If you just do like that, like the chances of breaking your arm. is good.
Yeah, like you like twist your shoulder basically. That's all. If you do like
See then.
How long you guys think?
An arm wrestle is
10 minutes
literally
to
also
scrap
like
a few off.
Like you use your legs, you
I'll
try
settle
back,
I'll with you guys. Are you
you
getting
generally
food?
hold
I
on
already
to
got
the
food.
leverage, and then you kind of like
Is that free food there?
Because like if you do just arms, most of the
I'm
time
not a serious arm
it's
wrestler.
like you'll come up with an injury if you do it like that.
Some light
That's why.
reading in the
Like
meantime.
we're not doing this like because of physics. It's like the reason it's
Running?
how it is.
I'm
is
doing
because
eigenvectors.
it's otherwise it will cause
In
injury.
3 courses that I'm doing right
Like
now.
it's
They come with a teachable
because of the
model,
reason.
right?
Not just like
It's
oh,
called
we just want to make it look
everything in
good.
quantum mechanics is
Yeah.
eigenvector.
So like I think it is if you want to try arm wrestling, you
No,
should
no, eigenstate. Like eigenfunction.
Eigenspace.
Yeah, eigenspace. The
Yeah,
eigenspace. It's a
Yeah.
it's a space spanned by all the eigenvectors. In quantum mechanics, the eigenvectors are a orthonormal
Wait,
basis.
so what's your name? Sorry.
William. This guy got 0.98 time.
Point nine.
Oh, god damn.
He got 10K. He got the money.
I was so close to the 10K, bro.
So close, so good.
Are you guys all like MathSoc?
Yeah.
think
Except
she's in the
him.
stream now.
He's just here.
In stream.
I mean, why didn't you try it for MathSoc?